Hi, we're on page 22 of the booklet. This is where we finished off last lesson with example 4, expressing the following in mod arg form. This is just an alternative method using exact values. So because we can see the root 3 there, we can write that as root 3 on 2. And because that's over 2, this needs to be over 2. So this is I on 2, or a half times I. And to balance out those divide by 2's, we put a 2 out the front. Now this is this needs to be cos and this needs to be sine. So this would be sine 30 is a half, and just one sec. And we know that cos 30 is root 3 on 2, but because it's negative, it's a quadrant 2 angle. So if the acute angle, we know that the acute angle is 30, but we know that this would be cos theta here. This is negative, so it's definitely quadrant 2. We know that sine of 150, so sine of 30 is a half, but sine of 150 is also a half because sine is positive in quadrant 2. So therefore our actual angle, theta will be 150 degrees because it's a quadrant 2 angle. And 150 in terms of pi, that's 5 lots of 30, which is 5 pi on 6. So therefore now this can be written as 2 times cos of 150 degrees plus I sine 150 degrees. And if we want to write that in radians, it's 2 times cos of 5 pi on 6 plus I sine 5 pi on 6. So therefore we can see that the modulus of z here, if z equals our complex number, modulus of z is 2, and the argument of z, I should put a capital A there because it's the principal argument of z, is 5 pi on 6. Okay, now with our second one, I'm going to take out 2 as a common factor first before we start, and then we'll keep the 2 out there. We can make these both 1 on root 2 and I on root 2. So to balance that out, we'll multiply here by root 2. We've got 1 on root 2 plus I, 1I on root 2. Now looking at they're both positive here, so we must be in quadrant 1. We know that sine of 45 degrees is 1 on root 2, and cos of 45 degrees is also 1 on root 2, so we can just put that on the side there. That's our thinking with this question. And we know that 1 on root 2, 45 degrees is also the same as pi on 4. So therefore this will be written as 2 root 2 cos of pi on 4 plus I sine pi on 4. Okay, so therefore the modulus of z is 2 root 2, and the argument of z, the principal argument, is pi on 4. Now you don't have to use this method here. It'll only work out for angles, related angles to 30 degrees, 45 and 60 degrees. It won't work for other angles. So you're probably just better off using, but you may come across it, so it's good to know that method. Now with example 5, expressing minus 2 minus 6i in mod arg form, you'll just do that your normal way. Of course, you need to sketch it first. So minus 2 minus 6i, that's quadrant 3. Okay, so you'll need to work out this angle here. So looking at our right angle triangle, we've got 2 and 6. So therefore, r is the square root of x squared plus y squared, which is the square root of 2 squared plus 6 squared, which is the square root of 4 plus 36, in other words, the square root of 40. And you can simplify that to 2 root 10. And we've got the tan theta is opposite over hypotenuse, it's 3 on 2. So 6 on 2, which equals 3. Therefore, theta is tan to the minus 1 of 3. Now, you can leave it like that as an exact value, or you can work it out with your calculator. The calculator, we get 71 degrees, 34 minutes to the closest minute. And so therefore, a complex number z is 2 root 10 cos of 71 degrees 34 minutes plus I sine 71 degrees 34 minutes, or if it's going to be written in the exact form, it could be written as 2 root 10. Here we could write that again in cis form, 2 root 10 cis 71 degrees 34 minutes is just quicker than writing the cos 71 degrees 34 minutes plus the I sine 71 degrees 34 minutes. Or we can write it in exact format as 2 root 10 cis, in brackets, tan to the minus 1 of 3. And that's the exact way of writing that. For 6, to express this complex number here in Cartesian form, it'll just be basically the opposite of what we did up in example 5. Okay, so we've got 2. Now we just evaluate cos 2 pi on 3. Now we know that 2 pi on 3 is 120 degrees, so it's really like you're working out cos of 120 degrees and also sine of 120. So we've got 120 here. So the acute angle, the related acute angle is 60. It's quadrant 2. We know that cos of 60, so this is going to be the same as minus cos 60 plus I sine 60. Now cos of 60 is a half, so it's 2 times negative a half plus I times root 3 on 2. Okay, we multiply through by 2 and we'll get negative 1 plus root 3I. Sorry, that's just off screen. I'll just fix that. And you could also see that written as root 3I minus 1. Okay. 23, multiplication in modulus argument form. If we express complex numbers in modulus argument form, we can obtain a simple expression for the product of those complex numbers. So if our first complex number Z1 is R1 cis theta 1 and Z2 is R2 cis theta 2, then Z1 times Z2 will be R1 cis theta 1 times R2 cis theta 2. Which is so we'll multiply the R1 and R2 and we get R1 R2, and we're expanding here the cis theta 1, which is cos theta 1 plus I sine theta 1, and here we're expanding the cis theta 2, which is cos theta 2 plus I sine theta 2. Now to expand this, I'm just going to multiply this out first, and we would get cos theta 1 cos theta 2 plus I cos theta 1, sorry, I cos theta 1 sine theta 2 plus I sine theta 1 cos theta 2 plus I squared sine theta 1 sine theta 2. Now let's just put the real parts together. We know that I squared is negative 1, so this will become, so that here we've got this cos theta 1 cos theta 2, and then we'll get minus sine theta 1 sine theta 2, and then we've got I as a common factor in these two, and we've got cos theta 1 sine theta 1 plus sine theta 1 cos theta 2. Now these are our double angle results from extension 1. So this is R1, R2. Now cos theta 1 cos theta 2 minus sine theta 1 sine theta 2 is just cos of theta 1 plus theta 2 with sums of angles. And this one here as well, sorry, there's meant to be a 2 there. This is the sine addition of, with the sums and differences, it's the sine result. So it's plus I sine theta 1 plus theta 2. So now writing this in a more condensed format, we can write it as R1 R2 times cis of theta 1 plus theta 2. So therefore our final answer here is a complex number in mod arg form with modulus R1 R2 and argument theta 1 plus theta 2. So notice that, or note that when we add theta 1 and theta 2 together, we're more than likely going to, or sometimes going to, get a result that is bigger than pi, or smaller than negative pi. So we'll need to add or subtract a multiple of 2 pi to obtain the principal argument, because the principal argument is always between negative pi and positive pi. Okay, so just keep that in mind when you're multiplying in mod arg form. So again, in summary, if we're multiplying two complex numbers, the modulus of a product is the product of the moduli. So the modulus of Z1, Z2 is R1 times R2, which is the modulus of Z1 times the modulus of Z2. And the argument of the product, Z1, Z2, is the sum of the arguments. So the argument of Z1 times Z2 is the argument of Z1 plus the argument of Z2. Now to look at an example. If Z1 equals 2 cis 2 pi on 3 and Z2 is root 2 cis 3 pi on 4, find Z1 times Z2 in mod arg form and also in Cartesian form, and then hence find the exact value of cos 5 pi on 12. Okay, we're going to start by expressing Z1, Z2 in mod arg form first. So we've got Z1 times Z2 is equal to, now I want to multiply the moduli, and I get 2 root 2, and then we'll add the argument. So we've got cos 2 pi on 3 plus, sorry, that's a plus 3 pi on 4, plus I sine 2 pi on 3 plus 3 pi on 4. Now, cos 2 pi on 3, we have to add 2 pi on 3 and 3 pi on 4. Now to add those, you can just add on your calculator 2/3 plus 3/4, and you will get on your calculator 17 on 12. So we write it as 17 pi on 12 plus I sine 17 pi on 12. Now we know that 17 pi on 12 is obviously beyond, it's beyond 1 pi. Okay, so we need to subtract 2 pi. So just over here, I'm just going to show that we're going to be doing 17 on 12 pi minus 2 pi. So on your calc, you can just do 17 on 12 minus 2. So 17 on 12 minus 2, and you get minus 7/12. So therefore, cos of 17 pi on 12 is the same as cos of minus 7 pi on 12, and same with the sine angle there. So we've got 2 root 2 cos of negative 7 pi on 12 plus I sine negative 7 pi on 12. Okay, now to find Z1 times Z2 in Cartesian form. So we've got Z1 times Z2 in Cartesian form. Now, because these are not exact values, you can't get an exact value for the minus 7 pi on 12 or the 17 pi on 12. You'll need to express each complex number firstly in Cartesian form and then multiply. Okay, because the original Z1 and Z2 are in forms that have exact values. Okay, so we've got the first complex number Z1 is 2 cos 2 pi on 3 plus I sine 2 pi on 3, which is 2 times, that's the cos of 120, which is the same as minus cos 60, which is 2 times negative a half, and this is the sine of 120, which is the same as sine 60, which is root 3 on 2. So we've got 2 times negative a half plus root 3 on 2i, which gives us, multiplying through by 2, we get negative 1 plus root 3i. That's our first complex number. Our second complex number, Z2, is root 2 cos of 3 pi on 4 plus I sine 3 pi on 4. And 3 pi on 4 is 145 degrees. This is the same as minus cos 45, and this is the same as sine 45. So this will be root 2 minus 1 on root 2 plus I times 1 on root 2, or I on root 2. Multiplying through there, we get negative 1 plus I. Okay, so now we can work out Z1 times Z2. That will be just negative 1 plus root 3i times negative 1 plus I, and multiplying through there, expanding the brackets, you get 1 minus I minus root 3I plus root 3I squared, which is 1 minus root 3 minus I bracket. Actually, I'll do it as a plus I, because it really is cos theta plus I sine theta. So we go plus I, looking at the two terms with an I, minus 1 minus root 3. So just as I said before, this has to be in the format of x plus IY. We don't want a minus there, okay? And so therefore, we can say that 2 root 2 cos minus 7 pi on 12 plus I sine minus 7 pi on 12 is equal to, so that's, need brackets there, is equal to 1 minus root 3 plus I minus 1 minus root 3. Now we need to equate real and imaginary parts. Okay, first we'll just start with equating real parts, because that may just give us our answer first. Okay, so equating real parts first, we've got that 2 root 2 cos of minus 7 pi on 12 is equal to 1 minus root 3. So therefore, oh sorry, I've just run off the screen there. So therefore we can say that cos of minus 7 pi on 12 is equal to 1 minus root 3 over 2 root 2. Now remember that we're trying to find, so we've got cos of minus 7 pi on 12 is 1 minus root 3 all over 2 root 2. Now we need to rewrite cos of minus 7 pi on 12 because we're trying to find cos of 5 pi on 12. Now if I just do a very quick sketch of where 7 pi on 12 is, well, minus 7 pi on 12, it would be, say, here, okay? So this would be 7 pi on 12, and this bit in here would be 5 pi on 12. Sorry, that's minus 7 pi on 12. If I look up here, this would be plus 7 pi on 12, and this little bit in here is also 5 pi on 12. Now, we know that 7 pi on 12 is quadrant 2. Remember, all stations to central. We know that cos is only positive in quadrants 1 and 4. So cos of minus 7 pi on 12, it will actually give us the same answer as, cos of minus 7 pi on 12 will give us the same answer as cos 7 pi on 12, which will then give us this related, or actually I can just do it from here. Cos of minus 7 pi on 12 is the same as minus cos 5 pi on 12 if I just look here. So I'll just do that. So cos of minus 7 pi on 12 is just the same as minus cos 5 pi on 12. Because it's quadrant 3, I actually don't need that up there. So therefore, I can say that therefore minus cos of 5 pi on 12 is equal to 1 minus root 3 over 2 root 2. And so, therefore, cos of 5 pi on 12, just multiplying the other side by negative 1, would be root 3 minus 1 over 2 root 2. And if I want to rationalize the denominator there, I can just multiply by root 2 over root 2, okay? And I will get root 6 minus root 2 over 2 times root 2 squared, which is 2 times root 2 squared, which happens to be 4. So I've got root 6 minus root 2 on 4. So therefore the cos of 5 pi on 12 is equal to that, root 6 minus root 2 on 4. For quotients in modulus argument form, now if we express complex numbers in modulus argument form, we can obtain a simple expression for the quotients or division of complex numbers. So if Z1 is R1 cos theta 1 plus I sine theta 1, and Z2 is R2, sorry, this is meant to be a cos, so if you can fix that, cos theta 2 plus I sine theta 2, then Z1 on Z2 will be, you know, whatever Z1 is over whatever Z2 is. Now remember, when we divide complex numbers, we need to realize as opposed to rationalize, so, or the equivalent sort of thing of rationalizing. So we need to realize the denominator. So we'll just do that. So r1 cos theta 1 plus I sine theta 1 over r2 cos theta 2 plus I sine theta 2. Now we'll times that by, we don't need to times it by the r2, just cos theta 2 minus I sine theta 2. It's just the conjugate complex over cos theta 2 minus I sine theta 2. So we want the conjugate complex of the denominator. Now we can expand that and we will get r1 over r2. And looking at the denominator, we've got a difference of 2 squares. So we'll get cos squared theta 2 minus I squared sine theta 2, I squared sine squared theta 2. And on the numerator, we've got r1, then we've got cos theta 1 cos theta 2 minus cos minus I cos theta 1 sine theta 2. Then we've got plus I sine theta 1 cos theta 2. And then we've got minus I squared sine theta 1 sine theta 2. Now, here we've got r1 over r2. With our denominator here, we'll end up with cos squared theta on 2 minus negative 1 is plus sine squared theta on 2. Now we know that that denominator is equal to 1 because that's that's a form of cos squared theta plus sine squared theta. So that equals 1. So we'll still have the r1 on r2. This all equals 1. And we'll just see what we've got for our numerator here. We've got cos theta 1 cos theta 2 plus sine theta 1. So here we'll have cos theta 1 cos theta 2 plus sine theta 1 sine theta 2. So I'm just going to need some more room here. And then we're going to get plus I, and we're going to have sine theta 1 cos theta 2 minus cos theta 1 sine theta 2. Now looking at our extension 1 results with sums and differences of angles, this is the difference for cos. So we've got the r1 over r2, then we've got cos of theta 1 minus theta 2. Sorry, I've just run out of room there. And then we've got plus I sine. Actually, I'll just move it up here. So as I was saying, r1 on r2, cos of theta 1 minus theta 2 plus I sine, and this is with the sine result difference, sine of theta 1 minus theta 2. So therefore we can see, let's come down here, that this is equal to r1 over r2 cis of theta 1 minus theta 2. So therefore, when you are dividing complex numbers in modulus argument form, the result will be a complex number with modulus r1 over r2 and argument theta 1 minus theta 2. In other words, what we do is we divide the moduli. So notice again that arg1 z1 minus arg z2 may not be the principal value, and you need to add or subtract a multiple of 2 pi to obtain your principal argument. So therefore, in summary here, dividing two complex numbers will give us that. So therefore the modulus will be the quotient or the division of the moduli. So modulus of z1 over z2 is r1 over r2, which is the modulus of z1 over the modulus of z2. Notice this is the modulus of z1 over z2. So it contains both of them, just showing that you can do the modulus of z1 divided by the modulus of z2, and the argument will be the difference in the argument. So you'll do argument of z1 minus argument of z2. Now, with this example. Now, with example 1, if z1 equals 1 plus I and z2 equals root 3 minus I, find z1 on z2 in mod arg form. Look, you can do this a few different ways because these are, if you go and multiply these, we may not end up with exact values later for the cos and the sine. So we really need to express each in mod arg form first. Now we're going to use the method that we used before, where we're using exact values, or we could just draw them, but I'm going to just practice, we can just practice that exact values method again. Now if we look at 1 plus I, we can write that as 1 on root 2 plus 1I on root 2, and we'll balance that out with the root 2 at the front. Okay, so therefore z1 is 2 times, we know that that's the cos of pi on 4, or cos of 45 degrees, plus I times the sine of pi on 4, or 45 degrees. And z2 is root 3 minus I. Now we know that the exact value would have to be root 3 on 2, and this would have to be minus 1I on 2. So therefore you balance this out with a 2 at the front. Now we've got root 3 on 2, this is positive here, and minus a half, we're getting a negative answer here. So for the cos to be positive and the sine component to be negative, you have to be in quadrant 4. Okay, so I'm going to do a little sketch here. Actually, we know that we're in quadrant 4 anyway, because actually it's probably a good idea to do a little sketch. With the first one, 1 plus I, you're definitely in quadrant 1. So that would be 1 plus I. And with this one here, root 3 minus I, so root 3 minus I, you are definitely in quadrant 4. So our angle is going to have to be a quadrant 4 angle. Now, of course, you can do this the other way, using your r is square root of x squared plus y squared. So for looking for cos of what is root 3 on 2, that would be cos 30. So this angle in here must be 30 degrees. So therefore it would be 2. Remember, it's a negative angle, so we've got minus 30 or minus pi on 6. So we've got 2 times cos of minus pi on 6 plus I times the sine of minus pi on 6. Okay, so now we've expressed both of those in mod arg form. So now we have to do our division of our complex numbers. So just remembering, when dividing complex numbers, divide the moduli and subtract the arguments. So therefore z1 over z2 will be root 2 on 2, and then we would do cis of pi on 4 minus pi on 6. So just be careful. It's the moduli of the first one, take away the modulus of the second complex number. So it's pi on 4, take away minus pi on 6. Now that is the same as root 2 on 2. Actually, I'll write that here. Root 2 on 2 cis. Now you can just do a quarter plus 1/6 on your calculator, or you can just work it out in your head. And we get 5 on 12. So this will be cis of 5 pi on 12. So therefore we've got root 2 on 2. You can leave it in that form with cis, or we can write it as cos 5 pi on 12 plus I sine 5 pi on 12. Okay, and therefore we're expressing that z1 on z2 in mod arg form. Looking at some special results. Now z times z bar is modulus of z squared. Now the proof of that, if we let z equal x plus iy, therefore z bar, or the conjugate of z, will be x minus iy. So therefore if we want to multiply z by z bar, we get, I'll just focus in on that a bit more. We get z times z bar is x plus iy times x minus iy. Now expanding that, we've got a difference of 2 squares. So we get x squared minus I squared y squared, which will be x squared plus y squared. Now we know that x squared plus y squared is the square root of x squared plus y squared all squared. The reason we're writing it in this format is that we know that the square root of x squared plus y squared is defined as the modulus of z. So it's the modulus of z squared, which equals this right-hand side here. Now, a second result. If z equals r cos theta plus I sine theta, in other words, that's the same as r cis theta, then the conjugate z bar will be r times cis minus theta. Now here's the proof for that. If z equals r cos theta plus I sine theta, then z bar is equal to r cos theta minus I sine theta. Now, these are quadrant 1 angles. Now we know that cos, all stations to central, we know that cos of theta is the same as cos of minus theta. So in quadrant 4, so we've got, we can say that cos theta is the same as cos of minus theta because that is quadrant 1 and quadrant 4, cos is positive. So we're just replacing the theta here with a minus theta. So therefore that equals cos of minus theta, but we're just keeping this the same, minus I times sine of theta, because we know that sine is negative in quadrant 4. Now what we can do here is, if we want minus I times sine of an angle, that's like saying plus I times the sine of that angle in quadrant 4. Because if we do sine of minus theta, that's the same as, so we know with the sine of minus theta is the same as the minus of sine theta. Sorry, just running out of room there. Okay, because it's a quadrant 4 angle. So here we're replacing the sine theta with a minus. So here, sorry, I've got sine of minus theta equals minus sine theta, which would mean that minus sine of minus theta equals sine theta. So here I'm replacing this sine theta with a minus sine of minus theta to get this line here. Okay, so now this can be written in cis form because the cos of this angle is the same as the sine of this angle. So we can write this as r cis negative theta. So this is another result. So z bar, or the conjugate, is r cis minus theta. If z equals r cis theta, then z bar equals r cis negative theta, or minus theta. Now, another result here. If z equals r cis theta, or r cos theta plus I sine theta, then 1 on z, which is the same as z to the minus 1, is equal to 1 on r cis minus theta. Now, there are two proofs here. The first proof, we know that if we've got 1 on z, what we do is we realise the denominator by multiplying by mod z, sorry, not mod z, bars, z bar over z bar, or the conjugate of z over the conjugate of z. Now, doing that, we get 1 times z bar is z bar, and using the special result from up there, this is a z bar, by the way, we've got z times z bar, we know is the modulus of z squared. Now we know from the result above as well that z bar, if I look up here, sorry, so looking at these results, we've actually, with this last one, just used that early result that was just proven. So coming back down here, z times z bar, we know is modulus of z squared. So we've replaced that with that. Z bar is the same as r cis minus theta, so that's been replaced with that there. So we've got r cis minus theta. We know that modulus of z squared is the same as r squared here. So therefore, we've got r on r squared is 1 on r cis minus theta. So that's another result that you need to learn. The other method is to do it like this, that 1 on z is equal to 1 cis 0. Now cis 0, sorry, just need to move that down. Cis of 0 is the same as cos 0 plus I sine 0. Now cos of 0 is 1 and sine of 0 is 0, so it's 1 plus 0, which is just 1. Okay, so that's why 1 is equal to 1 cis 0. Okay, and we know that z equals r cis theta. So doing this by division, where we're dividing two complex numbers, we divide the moduli, so it's 1 over r, and we subtract the arguments, and we get cis of 0 minus theta. Now 0 minus theta is minus theta or negative theta, so it's 1 on r cis of minus theta. Now, so it'd be a good idea to know these proofs, and you also obviously have to know these results because there'll be times when you will need to use them. Okay. Now, the last special result that we're going to look at is de Morris theorem. So we use de Morris theorem when we've got powers with complex numbers in mod arg form. Okay, actually I'm going to leave that, I think, for the next video. So I'm just going to stop this video now. The next video will start from de Morris theorem.